Report.
Alright, so I'm going to give you guys a little introduction and background to the Chandler study that we read. And this study analyzed a unique reef system in Palau, but I'm going to take a step back and look at ocean acidification in general and how it affects seawater chemistry and hurricanes. So we already went over this in the last presentation, but we have a double review on ocean acidification.
This is beautiful. Did you make this or did you steal it off the web?
It's stolen off the web.
Oh, that sounds great. I want to steal it from you.
So, oceans, as you guys all know, are a big sink for carbon dioxide in the carbon cycle, as they absorb 30% of atmospheric carbon dioxide. And the increase in carbon dioxide due to human impacts, as we've established, has led to the oceans becoming more acidic. So this figure shows the chemistry behind how increased carbon dioxide makes the seawater more acidic. So you start with dissolved carbon dioxide plus water forms carbonic acid, which is a really weak acid, so it quickly associates into hydrogen ions and bicarbonate ions. And these bicarbonate ions can also dissociate into more hydrogen ions and carbonate ions. So the big picture here is that more carbon dioxide creates more concentration of hydrogen ions, and this has corresponded to a 30% increase in the concentration of hydrogen ions since the Industrial Revolution. So seawater also has a natural buffer, so as the concentration of hydrogen ion goes up, carbonate ions can uptake these hydrogens and form bicarbonate. And so this graph here shows how you increase concentration of CO2, you also decrease the concentration of carbonate because it's acting as a buffer. And this is significant because calcifying organisms such as hard corals need these carbonate ions to form their calcium carbonate skeletons. So calcium carbonate is formed from calcium the calcium ion and the carbonate ion. And as we learned in the previous presentation, calcium carbonate is a polymorph, so in its solid form, it can exist as two different crystal forms. We've got aragonite and calcite. So reefs, hard corals are the reef-building corals, and they're also called scleractinian or hermatypic corals, and these are distinct from soft corals because they build the reefs, they build the calcium carbonate, as the picture shows, those are some of their skeletons. So they can only build their skeleton in supersaturated water, which is above the aragonite saturation horizon, which is where the aragonite saturation is equal to 1. And above it, it's above 1, supersaturated, and below the horizon, it's below 1, and it's undersaturated. And then a little chemistry review. The aragonite saturation state is equal to the concentration of carbonate ions times the concentration of calcium ions all over the aragonite equilibrium coefficients. So an important part to notice here is that any changes in the concentration of carbonate is going to affect the aragonite saturation. So aragonite is more soluble in seawater than calcite, and this figure just shows globally how the saturation horizons of these two different forms of calcium carbonate differs throughout the oceans. So we've got the north-south latitude and the east-west altitude, and the colors represent the saturation horizon in the oceans, the depth of the saturation horizon in meters. So on the bottom we have calcite, and in general it's about 3,000 to 4,500 meters, and the exception is in the North Atlantic Ocean. You've got about 0 to 1,000 meter saturation depth. That's the exception. And then aragonite, in general, you've got much shallower saturation horizon from 0 meters to 1,500 meters, with an exception in the North Pacific. You've got about 30,000 meter saturation horizon. So this just illustrates the difference between the two. And then what does ocean acidification do to the aragonite saturation? Ocean acidification, as we showed before, lowers the concentration of the carbonate ion because it's acting as a buffer, and so the this decrease in the carbonate ion concentration is going to decrease the aragonite saturation, and it's also going to raise the saturation horizon and make it shallower. And this figure illustrates the sea surface, the aragonite saturation at sea surface temperature, or just the surface. So in 2000, you've got, well, first of all, the colors. The red represents undersaturation, and orange to blue is supersaturation, which is what you want for calcifying organisms. And so in 2000, you have most of the sea is supersaturated, and then in the projected models, it's supposed to, or they predict that it's going to become more and more undersaturated, so uninhabitable for calcifying organisms. And then another important thing that the cloud paper that we read talks about with regards to ocean acidification is DIC and TA. So DIC is dissolved in organic carbon, and this includes carbon dioxide, carbonic acid, bicarbonate ion, and the carbonate ion. And then TA is total alkalinity, or the measure of the bases, and the bases are the bicarbonate ion and the carbonate ion. And DIC and TA are indicators of net calcification of hard corals in the coral reefs. So net calcification is how they build their calcium carbonate skeletons. So when they're calcifying, they're building these skeletons, and they're decreasing the concentration of carbonate ion. So DIC and TA decrease in a 2-to-1 ratio, and this decrease in carbonate also decreases the aragonite concentration. Whereas in dilution, the reverse happens, and calcium carbonate is diluted back into the seawater, so this increases DIC and TA in a 2-to-1 ratio, and increases the aragonite saturation. Photosynthesis and respiration are also affect DIC and TA. They change, photosynthesis and respiration only change carbon dioxide, so isolated changes in DIC with no effect in TA indicate that photosynthesis and respiration are changing seawater chemistry. So photosynthesis, as we all know, consumes CO2, so this is going to decrease DIC and not affect TA. And then it's also going to increase aragonite saturation because consuming CO2 is going to increase carbonate. And then in respiration, the reverse happens. So these 3 studies are mentioned in the introduction, and they're all previous studies on how ocean acidification is going to affect hard corals. And all of these studies, these are just a few studies, they all show that it's going to have a very negative effect on corals. So in the first study by Crook et al. In 2011, they found that low aragonite saturation and low pH levels is going to lead to low species richness, and the colony sizes are going to be much smaller. And in the second study, they found that low aragonite saturation had a negative effect on reef development. And then in the third study, they found that reduced or low pH corresponded to a decline in coral diversity. So they're all showing that these ocean acidification is really reducing the health of coral reefs. And then this is a figure that shows the calcium carbonate skeleton disintegrating in more acidic conditions. And this is a recent study. It was published in 2015. And it is, in each row, the pH is becoming more and more acidic. So you've got 8.1, 7.9, and then 7.7. And then, you can't really see it that much. But in each column, you're getting a closer look at the skeleton. And then this one is from the lab of one of the authors, Ann Cohen, and she was also an author in the last paper. And this is the skeleton of a baby coral. And in her lab, she had different tanks with different carbonate ion concentrations. And on the far left, you've got the carbonate concentration of seawater today. And on the far right, you've got the concentration of the carbonate ion projected for 2,200, and it's not doing too well. So, yeah, now I'm going to turn it over to Kirsten.